This second video on astrophysics shows how we can classify different stars into types according to their physical properties, such as temperature and spectral characteristics. For this, you must understand how two important concepts are defined in astronomy: apparent brightness and luminosity of a star. As always on this channel, you can expect a clear and concise explanation of each topic. Please don't forget to click on the like button, subscribe to our channel and activate the notification bell. Your support is crucial for our channel's growth and enables us to continue creating quality content. Thank you in advance for your support. Every star apart from our Sun appears to us as a point in space. The only direct information that we can have about any particular star is its position and intensity of radiation received from it. In fact, all that we know about stars has been deduced by measuring the radiation they emit and distances between them. This radiation has two important pieces of information: intensity, related to brightness, and wavelength, related to the color. Knowing the distance to a star, we can use this information to calculate its temperature, radius, and the amount of energy it radiates per second. The Sun and other stars behave approximately like black bodies. Therefore, stars are assumed to radiate like black bodies. So, if you have not studied black body radiation yet, I suggest you take a look at the video that appears in the upper right corner of the screen before proceeding, because, basically, the equations that will appear below are equations that emerged from the study of black body radiation. We begin defining the luminosity of stars. The luminosity of a star is defined as the total power it radiates in the form of electromagnetic waves. It is measured in watts. If we regard stars to be black-body radiator, then luminosity of a star is given by the expression, where T is the temperature, sigma is the Stefan-Boltzmann constant, and R is the radius of a star. The luminosity of a star depends on its size and its temperature. Luminosity is measured in watts. However, because stars are very luminous, astronomers often use another measure. They measure luminosity in units of the Sun's luminosity. So it's a good idea to calculate the Sun's luminosity. Find the luminosity of the Sun, taking the Sun's surface temperature to be 5,800 kelvins and its radius to be 7 times 10 to the power of 8 meters. We take the above formula and replace the radius and temperature with the given values. The luminosity of other stars is normally coded as a multiple of this value. What we actually measure on the Earth with a telescope is not luminosity, but a different quantity called apparent brightness of a star. The apparent brightness of a star is defined as the power crossing an unit area at the Earth perpendicular to the path of the light. Thus, the equation for the apparent brightness of a light source is given by the luminosity divided by the surface area of a sphere, with radius equal to your distance from the light source. The unit is watts per square meter. The apparent brightness of a star, as observed on Earth, will depend on its luminosity and its distance from Earth. As the light from a star travels out into space, so it becomes spread over the surface of an imaginary sphere of radius d, the distance from the star. As light from a star spreads out, its energy covers larger and larger areas, causing the energy per unit area to decrease in an inverse square relationship. With more area to cover, the light from the star appears dimmer. Apparent brightness is easily measured. Astronomers have developed very accurate means of measuring apparent brightness using charge-coupled devices, in which the charge produced in a semiconductor is proportional to the number of photons received, and hence the apparent brightness. If we also know the distance to a star, as seen in the previous video, then we can determine its luminosity. Knowing the luminosity, we can determine its temperature, and the surface temperature of a star is important because it tells a lot about the nature of the star. Let's see how it works. To solve this example, we use the equation for apparent brightness. This value is usually referred to as the solar constant. Another important parameter of a star is its surface temperature, which can be determined from the spectrum of electromagnetic frequencies it emits. The energy radiated by a star is in the form of electromagnetic radiation and is distributed over an infinite range of wavelengths. A star is assumed to radiate like a black body. This means the intensity distribution of electromagnetic radiation they emit is the same as the characteristic pattern of the black body spectrum, as shown in the figure. The relationship between the maximum value of the wavelength and its temperature, Kelvin, is given by the Wien's displacement law. The maximum value of the wavelength of the spectrum of light emitted by a star is inversely proportional to its Kelvin temperature, T. That is, it is an empirical law that represents how the wavelength at which the radiation intensity is highest becomes lower as the surface gets hotter. Let's see how we can use the Wien's displacement law to find the temperature of a star. First, we will use Wien's law of displacement to find the temperature. Then, we will convert the distance from parsec to meters. Now we use the apparent brightness equation to find the luminosity of Barnard's star. We can calculate the radius directly from the luminosity formula, but in terms of the solar radius, it seems better to use the ratio between the luminosities. The energy radiated by a star is in the form of electromagnetic radiation and is distributed over an infinite range of wavelengths. The intensity wavelength distribution of a star, like the one in the bottom left corner, is its emission spectrum, which is a continuous spectrum and it depends only on the star's surface temperature. We know that light of different wavelengths produces different perceptions of color. The longest wavelengths produce the perception of red, while the shortest ones produce the perception of violet. To estimate the surface temperature of a star, we use the relationship between the temperature and the wavelength of light where its spectrum peaks, and the color of the star is mainly determined by the color corresponding this wavelength. Therefore, the color of a star is linked to its temperature. The most common way to classify a star is by their color. Stars are classified according to their temperature because stars with similar temperatures tend to share many other characteristics. Stars are divided into 7 spectral classes, denoted in order of decreasing temperature, arranged from hottest to coolest. Hotter stars are blue-white and cooler stars are yellow-red. Another important piece of information in a star's spectrum is its chemical composition. As the continuous blackbody spectrum emitted from a star passes through its cooler outer layers, some wavelengths will be absorbed by the atoms present. When the radiation is detected on Earth, the resulting spectrum comprises dark lines, undetected photons, characteristic of an absorption spectrum. Each dark line represents the absorption of light of a specific wavelength by a specific chemical element in the star's atmosphere. Because we know that every chemical element has its own unique spectrum, this information can be used to identify the elements present in the outer layers of a star. The table below shows the classification of stars by spectral class, including the prominent absorption lines in each class. If you want to know a little more about the emission spectrum and spectral lines, I recommend that you watch the video that appears in the upper right corner of the screen, where these topics are covered in detail.